Okay, so before we go to make the analogy mathematically, let me walk you through the analogy a second time to make it completely explicit, but still at a qualitative level. So we started our story of our LC circuit with an LC circuit in which there was all this positive charge on the upper plate and all this electric field energy in the capacitor. So the energy in the system is all stored in the electric field. And in the 801 example of a mass on a spring, that's analogous, in the analogy that we are drawing, that's analogous to having all of the energy of this harmonic 801 harmonic oscillator, all of this energy in potential energy of the spring. The spring is stretched, the mass is at rest, no kinetic energy, all potential. So the electric energy here is analogous to energy in the spring here. The displacement is maximum. X is at its maximum positive value. Q is at its maximum positive value here, the Q being the charge on the upper plate. Then we let the first chapter of the story unfold. This capacitor drives a current. This situation that I've drawn here doesn't just stay this way. Capacitor like this is going to drive a current. Inductor objects, back EMF. Magnetic field starts to build up in the inductor. You start to generate magnetic field energy in the inductor. And at the same time, the electric energy in the capacitor is dropping because as the current flows, it's taking the charge off the top plate. On the 801 side of the analogy, this is not a stable situation with a mass at rest at the end of a very stretched spring. That's not stable. The spring pulls the mass. So the potential energy in the spring gets less, but the kinetic energy of the mass is growing. And so after the first chapter of the story, on the 802 side, we have an empty capacitor, no charge left. I have a maximal current flowing through the inductor. All my energy is magnetic. That's analogous to the situation when the mass is back at x equals 0, means no potential energy in the spring, lots, the maximum, in fact, amount of kinetic energy in the mass. So the potential energy has become kinetic. The electric energy has become magnetic. So the electric energy is analogous to potential energy in the spring. The magnetic energy in the inductor is analogous to kinetic energy of the motion of the mass. But this too is not a stable situation. You can't just have this mass keep moving forever because it starts to compress the spring. The spring fights back. This too is not a stable situation. You can't just have a current in the inductor flowing forever because the current starts to put charge of the other sign on the capacitor and the capacitor fights back. And after the second chapter of the story, we're at this row where the energy is back to being all electric. I have a fully loaded capacitor, but now the top plate is negative. Up here, the top plate was positive. Here, I have a mass at rest. Mass at rest is analogous to no magnetic energy. And I have lots of potential energy. The spring is far from its equilibrium length. This time the spring is compressed. The fact that the spring has a lot of potential energy, but it's the X is the opposite sign of before, that's analogous to saying here the capacitor has a lot of electric energy, but the charge has the opposite sign of before. So charge is like displacement, potential energy over here. So charge over here is like displacement over here, electric energy here, potential energy in the spring there. Magnetic energy here is like motion over there. Current over here will be like the velocity of the mass over there. And okay, now chapter 3 of the story happens. In chapter 3 of the story, I have this full capacitor. That's not a stable situation. It starts to drive a current, but the current flows in the opposite direction around the circuit. It starts to build up a magnetic field in the inductor. The electric energy decreases, magnetic energy builds up. And we're now in the 801 story, we're back to a situation where the energy is all kinetic. No more potential energy left. The mass is moving, but it's moving that way. Here, no more electric energy left. The capacitor is empty. Lots of current flowing, but it's flowing up this way. Previously, at this stage in the story, the current was flowing down. Now the current is flowing up. That's the end of chapter 3. In the fourth chapter of the story, this current starts to build charge back up on the capacitor. It starts to build charge up with a positive sign on the top plate. That starts to fight against the current, reduces the current, and you end up, after 4 chapters, you end up back here where we started with lots of electric energy, no magnetic energy, lots of potential energy, no kinetic energy. So this is an analogy that can be made mathematical, which is what we're about to do. But if you understand it at the qualitative level, which in the way that I've just presented it, you're all set actually to understand the math, because the math then is completely analogous to math that you're familiar with from back in 801. Notice that what happens here is that this is a story in 4 chapters. One full period of the story takes the energy from electric to magnetic to electric to magnetic and then back to electric, or from potential to kinetic to potential to kinetic to back to potential. So the energy sloshes back and forth twice in one period of the full oscillation. And if you think about Q starts out positive, goes to 0, and then gets negative, and then goes to 0, and then is back to being positive. Or if you think about the current starts out 0, and then the current is maximal in value flowing downwards, then the current is 0, then the current is maximal in value flowing upwards through the inductor, and then the current is 0 again. So the charge and the current, their full period of their oscillation is the 4 chapters of the story. But the energy sloshing back, it goes from electric to magnetic to electric in half the period. And this mathematically is equivalent to saying that cos squared has half the period of cos, as we'll see when we do this all with math. But to end here, if you get this analogy, you understand LC circuits. What we need to do now is figure out, well, how long is that period, and how do I describe this with math? And is this analogy just hand-waving, or is there actually a precise mathematical analogy between the equations for one and the equations for the other? And the answer is yes, there is, and we'll do that next.